All right, in this video we are going to model some real world cubic functions, okay? And the function we're going to model is a volume function. So one of the things that companies will do if we're trying to make a box is to actually take a rectangular piece of cardboard and cut out the corners so that you can fold up the box. So what ends up happening is this part right here becomes the bottom of the box, and this is the side, the side, the side, and there's another side over here that you fold up, and basically you create a box that way. So what we're going to be working with is examples like this, where we are going to be cutting out a little rectangular, or actually we're starting with a rectangle here and then cutting out these little square pieces that we can then fold up the box to create something that actually would hold something, okay? So in the first example, we are starting with a rectangular piece of cardboard that measures 20 inches by 30 inches. To create the box, the company cuts out the square pieces, folds up the sides as shown. Okay. Now, I am absolutely 100% giving you this volume function. You do not need to create it, but basically what's happening is we have X, which would be the little square that we're cutting out of the box, little side. So we've got the height of X, and then we have a length and a width. So we have the 20 inches and we removed 2 X's because there's 2 little squares being cut out. And then we had 30 inches and we're removing 2 little X's because there's, again, 2 squares being cut out. So if we take length times width times height, in this case we've got this function, that would give us a volume. All right, so first thing is part A. Use technology to graph the volume function, sketch the graph below. So I am going to go ahead and pop up Desmos. Okay. If Desmos has anything in it, it does not. Great. So I was going to say I'll clear it out. All right. So I'm going to take this volume function and I'm not going to use v of x. I'm just going to use y is equal to, and I'm just going to write the rest of the function. So x times 20 minus 2x times 30 minus 2x. And the parentheses. Okay, do a quick check to make sure that your function's answered incorrectly. So y equals x times 20 minus 2x, 30 minus 2x. Okay, so I'm going to go ahead and make this part disappear. And it looks like I have a straight line. All right, I can see a red line here, but I can't see any of the rest of the curve. So I'm going to go ahead and just start pinching and pulling and moving Desmos around so I can see what the heck is going on with this graph. All right. Okay, I swear this thing is going to end eventually. Let me see if I can do this. Okay, this is kind of a mess here. But basically, I know what the cubic function looks like. All right. And clearly we've got some quite significant volume here. All right. So sketch it as best you can. All right. It's going to come up here. It's going to come back down and then bounce back up. All right. And I am not at all worried about having the right points in the right places here. We don't have to label anything on the sketch. I just want to make sure that when I look at this sketch, I'm looking at the right information. All right, so part B says to identify the maximum volume box that can be created. Now, you might say, well, wait a minute, it's a cubic function, so that volume could be infinite. The problem is at a certain point over here in your function, you're actually going to be eliminating more x's than you have possible. So because x is a value here and your maximum, you had a cardboard piece, I guess, piece of cardboard that was 20 by 30. So you could say, oh, well, eliminate, x is equal to 10. Well, if you eliminate 10 from both of the 20s, all right, so think about it this way. Let me go back to this function. if x is equal to 10 here, right? Well, 2 times 10 is 20. 20 minus 20, that's 0. That doesn't make any sense. All right, so you can't go any higher than 10, all right? And basically, if I look at, and I'm going to kind of go back to Desmos here and look at my graph, and I'm actually going to zoom in on the x-axis here. Basically, you've got 0 here to 10 here, and then there is this part that goes negative, which doesn't make any sense for volume, and then we come back over here. The problem is all of these values beyond 10 don't make any sense for our graph. So we wouldn't want to use any of those, all right? So I want to make sure that whatever I'm picking here for this maximum volume is between 0 and 10, all right? So this is where I'm going to use this graph. I'm going to just scroll, 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 and scroll some more. I know there was an upper limit here, all right, a maximum point. I swear it exists. I'm going to find it. All right. Getting closer, getting closer. There we go. All right. So I can see right here I have a relative maximum. So I'm going to go ahead and tap on the graph. I think there it goes, it highlighted. And I'm going to tap on that point. Okay. Now, that point I need to translate into valid information. Like, what makes sense here? So when we look at this information for our function, all right, we have a v of x function, and we have x. So every point is x v of x on our graph. So x is going to represent the side of a square removed, okay? So those are little squares that we're removing, and v of x represents the actual, I don't know why I just spelled volume with an A. All right, let's try that again. Volume of the box, okay? So when we look at this point, 3.924 and then 1056.306, all right, so what's the maximum volume? Well, the maximum volume is that 1056.306, and I'm going to give it units. This is going to be inches cubed, all right? Volume is a cubic function. And what size squares must be removed from the cardboard to create that maximum? Well, that's the x value. So what size squares? 3.924 inch squares. Okay, so that's the x value for this particular problem. All right, so that finishes example 1 here because that was all the information we were asked to find. Now, example number 2 is the exact same thing, except we're changing what kind of cardboard we're starting with. So over here it says we're creating from square pieces of cardboard that measure 20 inches by 20 inches. So now we have a new function, all right? So we've changed our function here. We've got this one right here, okay? And again, you don't need to know how to, we're not going to ask you to make this function. We're going to ask you to manipulate the function, okay, to actually use it. So I'm going to go ahead and come back over here to Desmos, open up my graph, and I'm going to kill this piece, right? I'm just going to take it out. And I'm going to replace it with this function. All right, so y equals x times 20 minus 2x squared. Okay, make sure I typed it in correctly. I did. And I'm going to go ahead and collapse this back over so I can see more of the graph. All right, now clearly I'm going to pinch because I'm losing, oh, there's part of my graph. Okay. So, use technology to graph the volume function, sketch the graph below. It's just a sketch, all right? Does not have to be perfect. I know I'm going to come up through the origin, coming up here somewhere around 600. I saw that it bounced off the x-axis and bounced back. Okay. So, what sized squares must be removed to make a box with a volume of exactly 400 square inches? All right. Now, I could absolutely come up here and say, oh, look, here's 400, and I can look and see what these points are, but I'm going to actually make Desmos do this for me. So I'm going to open back up the equations here. And I am going to make an equation here where I want y to equal 400. All right, that's the volume that I am looking for in this function. So I'm going to go ahead and collapse that back. And now if I zoom in here, I can see that my blue original curve here, and then there's this green line that goes across directly at 400. So let's go ahead and tap on that, and I can see these little gray dots appear. There's one of them. Okay. Now, some of these make sense, some of them don't. All right. So if I go here and I talk about removing a 1.33 inch square. So if I go up here, 20 minus 2 times 1.33, yeah, that makes sense. Okay. So I could absolutely remove a square of let's try again not in highlighter. All right, so 1.33 inches. Okay, I could remove that square. 5.874. Well, if I take 2 times 5.874, it's about 11 and change. So 20 minus 11, yeah, that still makes sense. All right, so 5.874 inches. However, if I come over to this last point here, this is 12.7. So 12.7 doubled, because times 2 here means I would have 25 and some decimals. So if I take 20 minus 25 and some decimals, I'm going to get a negative answer here. It doesn't make any sense when we're talking about the length and width of a box. You can't measure a box and tell me it's -3 anything or -25 anything. So this answer over here does not make any sense. So please do not include it. It doesn't work in this problem. So what size squares must be removed? Only these two answers make sense. So the 1.33 and the 5.874. Okay. All right, we've got one more example, and then I will do number 4 in the answer key, but not in the video. Just kind of keep it a little bit shorter. We're back to a rectangular piece of cardboard that measures 20 by 25. So let's go ahead and put that volume function in. So I'm going to come up here, open up the functions again. I'm going to eliminate both of these two by just hitting little X's. That takes them off my graph. So let's see, y equals x times 20 minus 2x times 25 minus 2x. Let me make sure my my function's correct here. All right, y equals 20 minus 2x, 25 minus 2x. Okay, I didn't hit anything weird this time. That's nice. So I'm going to collapse that back. All right, let's go down to the x-axis here. Let's pinch in. There we go. All right. So I'm hitting, all right, got it. So up, down, and up. Okay. So we've got the graph. We've got this packaging company is contacted with an order to create boxes with a volume of 825 square inches. What size squares must be removed to create a box with the requested volume? Okay. So I'm going to go and I am going to make a line here, right? Y is equal to 825. All right. Let's see what this graph looks like. Okay. So coming up here. All right, Houston, we've got a problem. So we have a relative maximum here, a little bit over 820. And we're asked about 825. Now, if we come over here and we actually figure out this point of intersection, this would require us to remove squares of 15.146 inches. So if I take 2 times that amount, that's a little bit more than 30. All right, I'm not going to worry too much about the decimals. It just gives me the idea. It's a little bit more than 30. So 20 minus 30 is -10. 25 minus 30 is -5. And again, you can't have a box with negative dimensions. It doesn't make sense. Mathematically, it just doesn't work. So this particular company, if they're looking to try to create a box with a volume of 825, they can't do that right now. They would need to change the size of cardboard that they're working with. So for this particular answer, it says, what size square must be removed? I'm going to keep it simple. The company cannot create the requested volume with, starting with, let me get the right words there. Okay. Starting with the 20 by 25 inch cardboard. There we go. Rectangle. So it's not going to matter. You can't make this volume. It just doesn't work for this particular situation. Now, obviously, the company could change the cardboard that they're working with. There's a lot of different ways to make this work. But just understand that when you have a situation like this, you can just tell me that it doesn't work. All right. And it's not like a trick question or anything. It's just making sure you understand that there are certain answers like this 15.146. It works for the function, but in the reality of the context that we're working with, it doesn't. Okay, so problem number 4 will be part of the key. I'm going to turn off the video at this point. As always, send me any questions or concerns that you have.